All right, today we're diving into one of nature's most incredible and, honestly, violent light shows. We're talking about the cosmic fireworks that blaze through our atmosphere, the science behind fireballs and bolides.
So, you've probably been there, right? You're outside at night, maybe just looking up, and then bam, for just a split second, this brilliant streak of light just tears across the darkness. It's way brighter, way faster than an ordinary shooting star, and it leaves you standing there thinking, what in the world did I just see? Well, you're about to find out. So, first things first, let's give that flash of light its proper name. I mean, it might look like a shooting star on steroids, but what you probably saw belongs to a very specific and much more impressive astronomical category.
The official term is a fireball, and that's not just a cool sounding name, it's a real scientific classification. It's for any meteor that shines at a magnitude of -3 or brighter. Now, to put that into perspective for you, that is brighter than the planet Venus, which is usually the brightest thing you can see in the night sky, besides the moon.
And because they're that bright, they can be seen across hundreds and hundreds of miles. Some are so incredibly powerful, they can actually be spotted in broad daylight. Just try to imagine that for a second. A flash so intense that it can briefly outshine the sun. That is the kind of raw cosmic power we are dealing with here.
Okay, so where do these incredible things even come from? To really understand what a fireball is, we have to rewind the clock a bit and trace its journey all the way from the cold, deep darkness of space. And it all starts with this, a meteoroid. This is the actual rock itself. It's a lonely fragment broken off from an asteroid or a comet, and it's just silently tumbling through the solar system, orbiting the sun. It could be anything from the size of a grain of sand to, say, a small car. Now, when that meteoroid's path happens to cross with Earth's, it slams into our atmosphere at absolutely insane speeds, and the streak of light that it creates, that is what we call a meteor, or what most people call a shooting star. So here's the key takeaway. You're not actually seeing the rock. You're seeing the glowing, superheated air that the rock is tearing through. And this brings us to one final, kind of nerdy, but really important distinction. A fireball is that super bright streak of light. But if that fireball ends its trip by exploding mid-air in one brilliant final flash, which, by the way, many of them do, it's technically called a bolide. So you can think of the fireball as the show and the bolide as the explosive grand finale. So what actually happens during that fiery plunge? I mean, this is where the real drama unfolds. The meteoroid's entry into our atmosphere is this incredibly violent battle between rock and air, and it's a battle the rock is always going to lose. It's a really violent step-by-step process. First, friction with the air heats the object up to thousands of degrees. Then, right in front of it, a bow shock forms. It's like a wall of compressed, superheated gas. This crazy heat causes ablation, which literally vaporizes the meteoroid's outer layers, stripping them away. The immense stress then causes it to start breaking apart, or fragmenting, into smaller pieces, which just increases the drag. And then finally, the moment of truth. Catastrophic disruption. This quote explains that final moment perfectly. See, the pressure on the front of the object is absolutely immense, but there's a near vacuum right behind it. And that massive difference in pressure literally tears the rock apart from the inside out. It's not some gentle burn-up. It's a violent, explosive disintegration. That final explosion isn't just for show. It releases a truly mind-boggling amount of energy, and it's something scientists can actually measure. The energy that gets released is so huge, it's often measured in kilotons. To give you an idea of the scale we're talking about, 1 kiloton is equal to over 4 trillion joules. Put it this way, that's the same explosive power as 1,000 tons of TNT. And all of that energy is created simply by converting the object's incredible speed into heat and light. So, how in the world do scientists measure this? I mean, it's not like they have to find the rock. The light itself tells the whole story. By analyzing the optical energy, basically just how bright the fireball was, they can use a formula to calculate the total impact energy of the event. The light becomes a direct clue to the power of that collision. So, okay, we've seen the event, we've measured its energy, but what do we actually learn from all this? Why do we spend time tracking these cosmic visitors in the first place? Well, this is the kind of data that US government sensors collect. Now just look at the difference here. Event A is pretty small, less than half a kiloton. But then look at Event C, over the Bering Sea. It unleashed 173 kilotons of energy.
That is more than 10 times the power of the atomic bomb dropped on Hiroshima, all from a rock hitting our atmosphere at 32 kilometers per second. It's staggering. And collecting all this data is absolutely vital. For one, any fragments that actually survive and hit the ground, those become meteorites, and they're like little time capsules from the early solar system that tell us what asteroids are made of. The data also helps us map out how often we get hit and by what size objects. And of course, in a world that completely depends on satellites, tracking all this cosmic traffic is crucial for protecting our technology up in orbit.
So, the next time you see that brilliant flash in the sky, remember what you're really watching. It's a cosmic traveler on its final, violent, and spectacular journey. It's a powerful reminder that our atmosphere is an incredible shield, silently protecting us from what is, essentially, a constant cosmic shooting gallery. And it really leaves you with a final thought, doesn't it? What else is out there, right now, on a collision course with Earth, just waiting to make its grand, fiery entrance?